So just like it was in double integrals, in triple integrals or triple iterated integrals, it can be very, very important to choose the right integration limits and integration orders, because you can go from something that's impossible to something that's not that bad at all, or you could go from maybe something that's really hard to really easy. But either way, it's important to know that you can. So let's take a look at this particular integral here, or iterated integral. We're going from 0 to the square root of pi over 2, from x to the square root of pi over 2, and from 1 to 3 of sine of y squared dx dy dz dy dx. So if I try to integrate this straight, what I'm going to get is, so this is constant relative to z, so I'm going to get 0 to square root of pi over 2, x to square root of pi over 2, z sine y squared dy dx from 1 to 3. When I plug in, I get 3 sine y squared minus 1 y sine y squared. So I get 0 square root of pi over 2 x to square root of pi over 2 of 2 sine y squared dy dx. And this is a problem because I don't know how to take the antiderivative of sine of y squared. Technically, they say that means it has no elementary antiderivative. Functionally, what that means is that there are ways to describe this in terms of like a power series. Using a Taylor series, you could do the Taylor expansion, and then you could integrate the Taylor expansion, but what you'd have is an infinite series as a function, and that's just not very practical to use for what we're trying to do here. So let's not make our lives harder. Let's make our lives easier. And let's think about this. Okay, so this is pretty much impossible for doing this directly in terms of y. So what we would like to do is rewrite this as a dx dy integral. So how can we take this and how can we change those limits? Well, if we take a look over here with these limits in this plane, what we see is that x goes from 0 to square root of pi over 2. So it goes from 0 to here. And y goes from whatever x is to the square root of pi over 2. So if the x value is currently this, y doesn't start until there and goes all the way to the square root of pi over 2. So that's how that strip works. So what if we instead drew the triangle this way? What if we let y vary for constant, the interval was, the bounds were constant numbers, and x was a function of y. So what if you took the same thing and you said, let me find a good color here and I'll promise I'll put it out. If I took, whatever y was and then figured out where x goes. So notice if I start with y, x still always starts at 0 and makes it all the way to that line. And what is that line? Well, it goes from 0 all the way to square root of square root of pi over 2. So it looks like it's the line y equals x. So then what we might want to do here is go from 0 to y. Yeah. I had to check my notes, man. Sometimes you just want to make sure you say things correctly. So in this particular case, instead of these limits, we say, okay, well, y goes from 0 to square root of pi over 2, and x goes from 0 to whatever y is. So in this case, this one started at x and finished out at the end. This one starts at 0 and finishes at what y is. It's the same idea, but now we swapped the limits, or we swapped the order of integration. But if you look at this piece, that's actually constant with respect to x. So when we take the antiderivative, we get 2x sine y squared from 0 to y dy. Well, when x is 0, this thing vanishes. So when x is y, it works. We get 0 to the square root of pi over 2, 2y sine y squared dy. And we should now then revisit the old bread and butter of integration, which is substitution. So we're going to let u equal y squared. Du is 2y dy. And then when y equals 0, u is still 0 because y squared is still 0. So when y is the square root of pi over 2, u is just pi over 2. So we have u du u du here, 1/2 u squared from 0 to pi over 2. Oh, I knew something felt wrong. That's a sign of you. See, again, this is why you have to have notes. Make sure you don't do something stupid. So, by the way, you could have chosen u to be like sine of y squared. I wouldn't recommend it, but you could, and you would end up with. You probably shouldn't, actually, because just waste some time here, right? If u was sine of y squared, then du would be cosine of y squared 2y dy. Now that's already taken care of up here, but what do we do with this? You'd have to draw a triangle, right? You'd have some sort of y squared and some sort of angle. It's probably a terrible idea. So sine of y squared is u, then that's like u1 square root of 1 minus u squared. Yeah, I can't see why that would be a good idea. So I take it back. Complete waste of your time. So instead of that, you end up with negative cosine of u. So then you end up with negative cosine of pi over 2 minus a negative, so plus cosine of 0. Cosine of pi over 2 is nothing. 1. So that's a lot of work to get 1, but ultimately the whole point on this is trying to realize that sometimes things are basically impossible. So let's go ahead and flip it and do something that's reasonable so we can get a good answer.